Jai Hind students, welcome to my YouTube channel. And in the previous lecture, we have discussed theoretically the meaning of electromotive force, the terminal potential difference, the relationship between EMF and TPD. In this session, in continuation with the previous lecture, what we'll do is, we'll discuss some numericals based on EMF and TPD. And students, you must remember, we have discussed that during discharging of a cell, the TPD is always less than that of EMF. While during the charging of a cell, that is when the current enters the positive terminal and leaves the negative terminal, then the TPD across the cell is found to be greater than that its EMF. So let's discuss these theoretical points in solving these numericals, right? So let's start with the first question. So first question is, students, just read the question carefully. This is the circuit given. These are the two cells of EMFs 10 volt and 2 volt having internal resistances of 1 ohm each. These are the external resistances connected. What we are supposed to do is, we are supposed to find out the terminal potential difference across each of the two cells. So V1 and V2 are to be found, right? So the circuit can be modified in this particular manner. Now look, this one is the dominating cell. It's of EMF 10 volt. It will be sending current along this direction and it will be sending current along this direction. So this cell being dominant, we can consider the net current to be flowing in the anti-clockwise, right? So suppose the current is flowing is I. The current flowing through the circuit is I. Like, so before doing any sort of calculation, we can easily conclude that across this cell, the current is leaving the positive terminal while it is entering the negative terminal. So TPD across cell 1 must be less than that of its EMF. While on the other hand, students, consider cell 2. Here the current is entering the positive terminal and it is leaving the negative terminal. So across cell E2, the TPD across the terminals of cell E2 must be greater than that of its EMF. This is through the theoretical knowledge that we can predict. Now let us mathematically try to justify it, right? So let's solve this equation. So what will be the net resistance, external resistance I am talking about? So let's find out the external resistance of the circuit. This is 6 ohm, this is 3 ohm and this is 4 ohm. So these two are in parallel. Parallel of 6 and 3 would be 6 into 3 divided by 6 plus 3. That is 18 by 9, so it will give us 2 ohm, right? So the resultant of 6 and 3 is 2 ohm. So 2 ohm and this is 4 ohm. Definitely they are connected in series. Therefore net external resistance, it is equal to 6 ohm. What about the net internal resistance? These two cells are connected in series. In series the resistances get added up. R net is equal to R1 plus R2. So it will become R1 plus R2. Since they are connected in series. So 1 plus 1, that will give us 2 ohm, right? Now let's determine the net current flowing through the circuit. As per the definition, net current is always given by net EMF divided by total resistance offered by the circuit, which will be equal to the sum of the external resistance and the internal resistance. Net EMF, students, it will be plus E1 plus minus E2. Why I have assigned negative sign over here? Because these two cells are opposing each other. They are sending current in the different directions. So, if the cell is sending current in the anti-clockwise direction, that I have assigned positive sign. So, if the cell sends current in the clockwise direction, that will be assigned negative sign. So, that is what I have done over here. Here, the two cells will be sending current through the circuit in the opposite direction, right? So, the dominating one, that I have assigned positive sign. The less dominant one, that I have assigned negative sign. So, the net EMF in the circuit would be E1 minus E2, right? So, net resistance, net external resistance plus net internal resistance. So what you get is E1, that is 10, minus E2, that is 2. In case the two cells were connected in the same order so as to send the current in the same direction, then the EMFs would have been got added up. But in this case, the net EMF would be given by the difference of the EMFs of the two individual cells because of they are connected in opposite manner, right? What about the net resistance? External resistance is 6, internal resistance is 2. So what you get is 8 by 8, that is 1 ampere. So the net current flowing through the circuit is 1 ampere. This is 1 ampere. This is the net current flowing through the circuit, right? So therefore, TPD across first cell. This one is the first cell and consider it to be the second one. So here, from the positive terminal, current is leaving out, right? So TPD would be less. So formula is TPD across the first cell would be V1 is equal to E1 minus I into R1. I is the net current flowing through the cell. So what we will get is E1. What is the EMF of this cell? 10 minus what is the net current flowing through the cell? It is 1. What is the internal resistance of this cell? That is 1. So it would be equal to 9 volt. So as we have already predicted, across the terminals of cell E1, TPD would be less than that of its EMF. That is what we obtained. Now TPD across the second cell, it will be given by V2 is equal to E2. Now look, here it is a case of charging. Actually the current is entering the positive terminal and it is leaving the negative terminal. So I will be replaced by minus I. So here what you get is plus IR. So EMF of this cell is 2 plus current flowing through the cell is 1 and internal resistance of this cell is 1 ohm. Isn't it? So what do you get? It is 3 volt. So look, over here the TPD across the second cell is greater than that of its EMF. So it is only in this case, which is the charging case, where the current enters the positive terminal and leaves the negative terminal. There only TPD can be greater than that of its EMF. Else in all the other normal conditions, in the case of discharging, TPD is always less than that of its EMF. So that's the result stories. These are the TPDs across cell 1 and cell 2 respectively, right? So we are over with the first portion. Now let's consider on the second one. Just students go through the second portion. Read the question very, very carefully. A battery of 24 cells. I have told you, combination of cells, that is known as a battery. Each of EMF 1.5 volt and internal resistance 2 ohm is to be connected in mixed grouping so as to send maximum current through the circuit. And the circuit contains an external resistance of 12 ohm. How are they to be connected? How many rows? And in each row, how many cells should be connected in series? Find the current in each cell and the potential difference across the external resistor. So there are 3 parts. It's a very, very interesting and very good question. So let's try to solve it. Total number of cells, which is equal to m into n. Students, you must remember, while doing the article, we have considered m rows and each row contain n cells. So total number of cells is m into n. And it is given to be 24, right? This is the first condition which is given to us. They are connected in mixed grouping so as to send maximum current through a 12 ohm resistor. It should be like this. These are the cells I am talking about. These are the cells. Some are connected in series and these branches are connected in parallel, like this. This is the mixed grouping. Let us consider there are m rows and each row contain n cells, isn't it? And the entire combination is connected across an external resistance of 12 ohm. This is given to be 12 ohm and this is the current. Okay, let's try to find out the maximum current. Now students, you remember, current from the mixed grouping of cells is maximum only when the net internal resistance offered by the mixed grouping of the cells is exactly equal to the next external resistance. This is the condition which we have derived in the theoretical part. We have to make use of this result while solving this numerical problem. So, for current to be maximum, net external resistance, it should be equal to the net internal resistance. This is the condition, right? So, net external resistance is 12 ohm. This is the net external resistance. And what is the net internal resistance? You must remember, in each branch, the net internal resistance would be NR. this is NR, this is NR, and these are connected in parallel. So you will use that formula 1 by R net is equal to 1 by R1 plus 1 by R2 plus 1 by 3 and so on. So net internal resistance would be NR divided by M. Clear, students? This is the net internal resistance in the mixed grouping of cells. Clear? So let's make use of these two equations. Right? Put this as equation number 2. And internal resistance is also given. I think it's given to be 2 ohm. So what to do is 12 is equal to N multiplied by 2 divided by M. So M and N are the two variables, and we have got two equations. We can easily solve 1 and 2 so as to obtain the value of M as well as N. Let's try it. So over here, what you get is 6 is equal to N by M. Now you can substitute the value of M as 24 by N. So N in place of M, you can write 24 by N. So what you get is N square is equal to 144, or N is equal to 12. So if N is equal to 12, which implies that M should be equal to 2, because their product is equal to 24, isn't it? So what we have obtained is, how the 24 cells are to be connected is, they are to be connected in such a manner so as to contain two rows. Each row containing 12 cells connected in series. So 2, these are the number of rows, and in each row 12 identical cells are to be connected in series. So that is how these 24 cells are to be connected so as to derive maximum current from the circuit or from the mixed grouping of cells. So I will draw that circuit. So this should be the appropriate circuit diagram, right? There should be 2 rows, and each row must contain 12 cells connected in series. These are 12 identical cells which are connected in series, and these are the 2 rows. And this is the external resistance, that is 12 ohm. So first part we have done. So how are they to be connected? 24 cells are to be connected in this particular manner, in the form of 2 rows, each row containing 12 cells connected in series. So this grouping, mixed grouping of cells, will be capable of giving maximum current, isn't it? Okay, let's deal with the second case. Find the current in each cell. We are supposed to find out the current in each cell, right? So what to do is, let's find out the net current first. Net current, student, it's equal to net EMF, right? And in the article, in the theory part, we have already derived it. We need to make use of the formula directly over here. What is the expression for the current obtained in the mixed grouping of cells? It is MNE divided by MR plus NR. M is the number of rows, N is the number of cells connected in series in each row. This is the formula which we have obtained theoretically, which we have already derived, right? M into N is the total number of cells. So let's discuss it. M is 12, N is 2, EMF of each cell, that is 1.5, M, it is 2, external resistance, that is 12, plus N, that is 12, and internal resistance, that is 2. So what do we get is, I would be equal to 24 multiplied by 1.5 divided by 24 plus 24, that is 48. So it would be equal to 1.5 divided by 2 ampere. So net current would be 0.75 ampere. So this is the net current flowing through the circuit, 0.75 ampere. This is the net current flowing through the circuit, 0.75 ampere, right? But we are supposed to find out the current in each cell. Now look, students, over here what happens is, the net current will get divided equally across these two branches, isn't it? Net charge is conserved, so accordingly, the sum of the current entering a junction, it must be exactly equal to the sum of the current leaving it. Net current entering is 0.75, so it will get equally divided. So in this case, the current would be 0.375, which is half of 0.75, and here also the current would be 0.375. Clear? These two currents will again combine together so as to form 0.75 ampere. So this is 0.375 ampere and this is also 0.375 ampere. So across each of the branches, each of these two rows, the current flowing is 0.375 ampere. Both the rows are offering the same resistance, therefore the current will get equally divided between these two branches. So it will be 0.75 divided by 2, which will be 0.375 ampere. Right? And since they are connected in series, the current across each of the cell would be constant. So find the current in each cell. This we have obtained. Through each cell, the current flowing is 0.375 ampere. Done, student? Last part. What is the potential difference across the external resistor? This is the external resistor. And what is the current flowing through it? 0.75. Therefore, potential difference across 12 ohm. Potential difference is I multiplied by R. What is the current flowing? 0.75. What is the value of the resistance? 12. So 0.75 is 3 by 4 multiplied by 12. So it will be 9 volt. So that's the answer. So the net PD potential difference across the external resistance is 9 volt. So students, this was a very, very important question containing 3 parts which we have done completely. Right? I hope you have understood this question. Now let's proceed to the third one. Again, third question is quite interesting one. You have to read the question, and if you are able to understand the question, I am very sure you will be easily able to find its solution. First try to understand the question. 50% of the question will itself get solved then. Okay, third one. 12 cells, each having the same EMF, are connected in series and are kept in a closed box. Some of the cells are wrongly connected. This battery of cells is connected in series with an ammeter and 2 cells are identical with others. The current is 3 ampere when the cells in the battery aid each other and is 2 ampere when they oppose each other. Right? How many cells in the battery are wrongly connected? Suppose this is a battery. This is a battery. Battery means combination of many cells. Right? It's a combination of many cells. So how many total cells are there? I think 12 cells. They constitute a battery. 1, 2, 3 and 11 and this is 12. There are 12 cells, right? Some of them are correctly connected and some of them are wrongly connected. Correctly connected means, wrongly connected means some of the cells are connected in such a manner so as to send current in the opposite direction. Clear, students? So, these all are connected correctly so as to send current in the same direction, while they are connected wrongly so as to send current in the different direction. Isn't it? So, what we are supposed to do is, how many cells in the battery are wrongly connected? So, what you do is, let X cells are connected correctly. Let X cells are connected correctly. Then, out of 12 cells, if X cells are connected correctly, then 12 minus X cells are wrongly connected. Clear, students? What we have assumed is, out of 12 cells, suppose X cells are connected correctly. Then 12 minus X cells must be connected wrongly. Okay, now let's read the question again. Some of the cells are wrongly connected. The battery of the cells is connected in series with an ammeter and 2 cells are identical with others. Right? So, suppose each has got an EMF of E. All cells are identical. And here, no internal resistance is given. So, we are supposed to assume that the internal resistance offered by each of the cell is negligible. So, it can be avoided. So, consider each of these cells to have EMF of capital E. Now when this battery is connected, when the battery is connected in series with an ammeter and two cells identical with each other. Okay, these are connected with two other cells in series along with an ammeter. Right? When the cells and the battery aid each other, then the current is 3 ampere. So these are the two cells. So net EMF would be 2E. When they aid each other means they will be connected in such a manner, these two cells will be connected in such a manner so as to send the current in the same direction as that of the battery. Isn't it? So let's construct the equation then. Net current is given to be 3 ampere. And suppose it is connected to an external resistor of R. This is the external resistor. This is R. And net current is I. Net current flowing is I, suppose. Okay, we are aware net EMF is equal to net current multiplied by net resistance. Here, internal resistance is considered to be negligible. So what about the net EMF? Net EMF, these two are aiding this entire battery. So net EMF of this battery. First of all, let's calculate the net EMF of this battery. X cells are connected correctly. So the EMF of X cells would be X times E. These are the cells which are wrongly connected. So it has to be subtracted. 12 minus X number of cells are wrongly connected. But again, all the cells are identical, each of having EMF E. Isn't it? This is the net EMF of the battery. Minus sign because these are the cells which are wrongly connected. And this battery, when connected with the other two cells, if they aid each other, then the current is found to be 3 ampere. So aiding means these two cells are sending current in the same direction as that of this battery. So plus twice E. So this will be the net EMF of the circuit. And net EMF of the circuit is equal to net current, which is considered to be I, multiplied by net resistance, that is R. And this current, student, it is given to be 3 ampere. So this is equation number 1. Clear, students? Okay. Now read the other one. And the battery aid each other and is 2 ampere when they oppose each other. If these two batteries are connected in such a manner so as to oppose the battery, then it will be like this. Now the equation would be, now the current gets reduced to 2 ampere in case these two cells oppose this battery. So the equation would be, the net EMF of the battery will remain same. But in this case, these two cells are opposing this battery. So it will be minus 2E. So this is the net EMF of the circuit. Net EMF of the circuit is equal to net current multiplied by net resistance. Now the net current flowing through the circuit is 2 ampere. And resistance R. Internal resistance is negligible. So students, these are the two equations. Now by solving these two equations, we can easily get the value of X, and accordingly we can easily get the value of number of cells which are connected wrongly in this particular battery. Right? So let's try to solve it. What to do is, if we divide these two equations, let's divide these two equations. E is common in both numerator as well as denominator. So we'll be left with X minus 12 minus X plus 2 divided by, over here we will be left with X minus 12 minus X minus 2, and over here we will get 3 by 2. Clear, students? Okay, let's keep on solving it. What we get is X plus X 2X minus 12 plus 12 will give us minus 10 divided by, over here again, 2X minus 12 minus 12 will give us minus 14 is equal to 3 by 2. Again 2 can be taken as common. So what we get is X minus 5 divided by X minus 7 is equal to 3 by 2. Clear? So let's try to solve this and get the value of X. X, students, remember we have assumed X to be the number of cells which are correctly connected. So what we get is, after cross multiplication we get 2 into X minus 5 is equal to 3 into X minus 7. So 2X minus 10 is equal to 3X minus 21, or 21 minus 10 is equal to 3X minus 2X. So X is equal to 11. So as I have told you, X is assumed to be the number of cells which are correctly connected. There were total 12 cells, out of which 11 cells are correctly connected. So the number of cells which are wrongly connected in the battery must be 1. Therefore, number of cells connected wrongly in the battery would be 12 minus 11, that is 1. So students, 1 is the answer. Out of the 12 cells, only 1 cell constituting the battery is wrongly connected. So please try this question again and repeat this question, understanding all the concepts involved. This is a very, very good question, and these are all selected questions actually, right? So do pay adequate attention while solving these questions and the concepts involved basically. Okay, let's proceed with the fourth question. Let's proceed with the fourth one. This is a circuit given. It is identical to that of the first question. So question 3rd is over. Let's try the fourth one. Okay. Find the TPD, terminal potential difference, across each of the cells. Now look, these are the 2 cells which are connected in the same order. This is a cell which is connected in the opposite order, isn't it? And what about the net resistance? 6 and 6 are in parallel, so effective resistance will be 3 ohm. So this will be the circuit. This is 2 volt, this is 2 volt, this is 2 volt, and each of internal resistance 1 ohm. Each cell is having an internal resistance of 1 ohm. And external resistance, these 2 are in parallel. The parallel resultant of 6 ohm would be 3 ohm. So let's find out the net current first. Net current through the circuit is, suppose these are the 3 cells. Net current through the circuit is net EMF divided by net resistance. What is the net EMF? These are the 2 currents sending in the same direction, while this is the cell sending current in the opposite direction. So it will be equal to plus E1 plus E2 plus minus E3. Why this negative sign? Because it is opposing these 2 cells. It is sending current in an opposite direction. Divided by net resistance. Net resistance is the external resistance plus internal resistance. Internal resistance, since the cells are connected in series, the net internal resistance will get added up. Clear, students? So let's solve it. E1, 2 plus 2 minus 2. Each of EMF 2 divided by 6. So what we get is 1 by 3 ampere. So this is the net current flowing through the circuit, flowing through each cell. Across each cell, this is the current flowing, right? Now let's find out the TPD across each cells. Now both these cells, 1 and 2, are identical and sending current in the same direction. So TPD across the first cell would be equal to the TPD across the second cell, and it would be equal to E1 or E2 minus I into R1. What is the EMF of these 2 cells? There is 2 volt. What is the current flowing through each of this cell? 1 by 3. What is the internal resistance? 1. So it will be equal to 2 minus 1 by 3. So 6 minus 1, that is 5 by 3 volt. This is the TPD, which obviously is less than that of 2 volt. Clear, students? So in this case, the current is leaving the positive terminal and it is entering the negative terminal. So TPD across the terminals of the cell should be less than that of its EMF. So 5 by 3, it's about 1.67 volt, which is less than 2 volt. So it validates that theoretical fact, isn't it? Now TPD across the third cell, it will be equal to E3 plus I into R3. Why this plus sign? Because here current is entering the positive terminal and it is leaving the negative terminal. It is the case of charging, where the TPD must be greater than that of its EMF. So what is E3 over here? Again 2 volt. Net current flowing through this cell is 1 by 3. Internal resistance offered by this cell is 1 ohm. So it will be 2 plus 1 by 3. It will be 7 by 3 volt, which is obviously greater than 2. So it again verifies the fact that the TPD is greater than EMF only if the current enters the positive terminal of that particular cell and leaves its negative terminal. Right, students? So I hope you have understood these questions, and we'll continue with some other conceptual questions in the next lecture. Till then, do take very good care of yourself and study very well and on a consistent basis. Good luck. Thank you.